Okay, welcome back. I'm going to continue the discussion of cosmic ray sources and radiative processes today. And let me start to share my screen with you. Okay, I hope you can see this. So, yesterday we talked, we finished, or I finished the lecture talking about core collapse supernova, which lead to supernova remnants, which are places in our galaxy where particle acceleration can occur. And so the type of remnants that we can observe these days look like this here. This is actually a supernova remnant, which was observed by Tycho Brahe 500 years ago, which was not originating from a core collapse supernova. There's an alternative mechanism for supernova, which is called a type 1a supernova, which is a thermonuclear explosion triggered by the accumulation of gas onto the surface of a white dwarf, which can trigger a thermonuclear explosion at a critical mass. But both of these supernova create remnants, and this is here a remnant from a type 1a supernova. And the colors that you see here in this astronomical image, this is taken from the Chandra satellite, which is observing X-rays. The different colors here are indicating different energies of the X-ray emission. And so X-ray emission here is in the region of kilo electron volt. Okay, so both types of these remnants are places where we think diffusive shock acceleration can occur. So diffusive shock acceleration is the first order Fermi acceleration that we briefly introduced yesterday. And this was also part of the first exercise sheet where we were looking for the particle acceleration and loss in the environment. And the goal of this exercise was to realize that this process allows to generate power law spectra. And then we had to put on one additional ingredient to relate the loss time and the acceleration time to derive the spectral index of the outcoming population of non-thermal electrons or cosmic rays. So you can also derive the same result in a very elegant way using the diffusion equation that I introduced earlier. And let me briefly walk you through this. So eventually, after the supernova explosion, you will have swept up enough material from the interstellar medium that you produce a collisionless shock. So the shock is collisionless here, meaning that you do not have intense particle interactions that could be a dissipative term leading to a loss of particles, but instead you have collective interactions of the plasma via magnetic fields. And so these magnetic fields will basically form this shock, but particles will not have strong interactions in the shock such that they will lose energy. So this is an ideal environment for cosmic ray acceleration. And so here in this sketch, I have tried to set up my coordinate system for our calculation. So you have the supernova remnant, which is on the right-hand side here at z equal infinity. And you have here the interstellar medium on the left-hand side at z equal minus infinity. And we have chosen a coordinate system where the shock between the interstellar medium and the shocked material is fixed at z equals 0. So we are basically choosing a coordinate system that is moving with the shock and keeping the shock at rest at z equals 0. Now, we have here the upstream region. So this is the region where interstellar material is flowing into the shock and slows down. And then we have a downstream region here, which we indicate by 2, where the bulk velocity is slowed down because you are in the shocked region. And the shock here is a discontinuity that divides the shocked and unshocked region. And we have different velocities here on both sides, so bulk velocities, bulk motion, but we also have different densities and pressures on both sides. Now, in this shock environment, we can now derive a relation between the velocities, the densities, and the pressures on both sides of the shock. And these relations are fixed by the continuity of mass, momentum, and energy. So we have the condition of mass conservation, which in the steady state case is looking like this here. We have momentum, which looks like this here, and we have the conservation of energy. And here the energy will be the total energy, which is divided between the bulk kinetic energy, this is basically the first term that you see here, and the internal energy, which is related to the pressure via the adiabatic index. So this factor gamma that I indicate here is the adiabatic index. And basically the pressure here is in an ideal gas is related to the internal energy via this, the adiabatic index gamma minus 1 times the energy. And for a monatomic ideal gas, the adiabatic index would be 5/3. So this is what we are going to use in the following. If you have a diatomic gas, you have more degrees of freedom. And in this case, the adiabatic index would be somewhat larger. It would be 7/5. But this here is the one that we are going to use in the following. So this set of conditions of mass, momentum, and energy conservation across the shock. So these are also called the Rankine Hugonot jump condition. So these conditions here are expressed in differential form. What we are going to do now is we are going to integrate across the shock. So we integrate here just below the shock on the left-hand side. So this is from 0 minus to 0 plus. So this is basically an epsilon, minus epsilon plus epsilon from left to right. We integrate over the shock. And then we can convert these gradients across the shock of mass, momentum, and energy to a relation between the conditions left and right of the shock. And this system of three conditions can then be solved for the density, the velocity, the pressure, and also the temperature on both sides. For us, what's going to be important is the pressure and the velocity. And let me bring up a new page here. So if you do this exercise and if you solve these equations, you will end up with the following condition. So solving the Rankine Hugonot jump condition gives you the following. So the densities between the shocked and unshocked region is the same as the ratio of the velocity in region 1, so the unshocked region divided by the shocked region. And this is given by the following expression, and this is also the expression that I provided in the first exercise on Tuesday. This is given as gamma plus 1 times the Mach number to the power 2 and gamma minus 1 Mach number to the power 2 plus 2. And the Mach number here is, so Mach number is defined here as the ratio of the the upstream velocity u1 divided by the sound speed. And if you recall from your thermodynamics course, the sound speed squared is defined as the derivative of pressure with respect to density. And this can be related to the adiabatic index. So this is going to be the adiabatic index times the pressure divided by the density. And so the sound speed is given as the square root of this combination. And in the case of a strong shock, meaning that the Mach number is much, much larger than 1, you can see that the ratio of the upstream velocity over the downstream velocity is going to be gamma plus 1 over gamma minus 1. So you can basically omit this additional factor 2 here. And if you now put in the adiabatic index of an ideal gas, this is 5/3 plus 1 over 5/3 minus 1. So this is simply 8/2 or equal to 4. So this is the limit in the case of strong shocks. This is going to become important later on when we talk about the spectral index. Okay, so we are now trying to derive the accelerated spectrum in this setup where we have a planar shock. So a setup like this here, we have a planar shock, which is located at z equals 0. And we assume that we basically have an infinite system. The supernova remnant is infinitely far away. And also here, the interstellar medium is infinitely far away on the left-hand side. And we can now look for the phase space density of cosmic rays in the vicinity of the plot. Vicinity of the shock. And so the stationary condition of the angular average phase space density. So this was the angular average phase space density, which is this quantity phi that I introduced in the first few lectures. So the stationary condition is the following. We have the convection term. And the problem is one-dimensional, so we only have one spatial variable z. And this is going to be given by the diffusion term. Again, just in one dimension. So I'm dropping the indices of the diffusion tensor here. So this is just the ZZ entry of the diffusion tensor. And then we have also a term which leads to energy loss across the shock, which is related to the compression of the fluid. So this is du over dz, and then p, and then the momentum derivative with respect to of the angular averaged phase space density. And then we also assume that we have a source term qzp. So this is here now the phase space, the stationary condition for the phase space density of cosmic rays in the vicinity of the shock. So we will assume in the following that particles are injected in the vicinity of the shock. So the term qzp is going to be q0p. So this is the initial spectrum of the particle injected at the shock. And then the injection will only happen in the vicinity of the shock. So we have a delta function here with z equals 0. Now, if we want to solve this equation, the start equation here, we have to look at 3 different regions. So we can first look here at the shock region. And to study this region, we again integrate the stationary solution between 0 minus, and 0 plus. So this would be minus epsilon, and this would be plus epsilon, where epsilon is going to 0 in the vicinity of the shock. So if we do this, then the term here on the left-hand side of this equation, this is going to be 0, because we assume that the gradient of the phase-space distribution is well behaved. It's not going to have any infinity. So this is here a finite number. And if we push the integration limit to 0, then this term here is going to give 0. However, this is not the case for the other terms that appear here on the right-hand side of this equation. So the right-hand side of this equation will give us the following condition. We have the diffusion term of the phase-space distribution just above the shock minus the one just below the shock. So below in the sense of z, the coordinate that we introduced. And yeah, we will assume that the derivative of, let me go back here, the derivative of the velocity across the shock is given as, so this expression here, du over dz, is going to be the difference between the two velocities, u2 minus u1. u2 minus u1 delta z. So there will be a jump in velocity across the shock according to the Rankine-Hugoniot jump conditions. So that means that the second term is going to give us the following. Integrating delta z from minus 0 to plus 0 simply gives us 1. So this will be 1/3 u2 minus u1, and then times p del phi over del p. And then we have the source term, which is also located at the shock. So this will simply give us q0, p, and this is equal to 0. So now we have to, so this is in the shock region, integrating over the shock region. We can now also look at the solution in the downstream region. So the downstream region was this region here in the direction of the supernova remnant. So in this direction, we will assume that due to the repeated scattering of cosmic rays in the plasma, the distribution will be, the spatial distribution will be flat. So in this region, we assume that del phi over del z in the entire region downstream is going to be equal to 0. And in particular, in the vicinity of the shock, which is the quantity evaluated at plus, this will be equal to 0. And you can convince yourself that this is also then a solution to the stationary condition of the angular average phase-space density. So this is done. And now in the upstream region, we have the following condition. So in the upstream region, we do not have to take care of the jump condition at the shock. So this is the region that extends from minus infinity to minus 0, so just below the shock. And this, the differential equation is reducing to just these two terms of the convection and the diffusion term. So if we are now integrate between minus infinity, so the boundary condition of the interstellar medium, and O minus, so just below the shock, then this will give us simply U phi minus K del phi del Z evaluated at 0, 1, so just below the shock, minus the So this is U1 here from the upstream region, minus the term from minus infinity. I should rather call this here -1, actually. So we assume now also that if we go far up in the upstream region, into the interstellar medium, then again the term which is given here on the right hand side is going to vanish. So this is going to be equal to 0. And that means we are, so this is also equal to 0. And that means that in the vicinity of the shock, just below the shock, we get the condition that K del phi del Z O minus is equal to U1 phi 0. And phi 0 here is going to be the cosmic ray distribution in the vicinity of the shock. Yeah. So these are the three different conditions that we can derive from the phase-space distribution, including also the jump condition that we have at the shock. And so the final differential equation that we derive this way looks then as follows. So combining these three different results, we arrive at the condition that U1 phi 0, the cosmic ray density in the vicinity of the shock, is going to be 1/3 U2 minus U1 P del phi 0 over del P plus Q0P. So the Q0P term, this was the injection of cosmic rays, the source term in the shock. And in the following, we will assume that the injection is happening from a cold distribution of particles which are flowing into the shock. And so this distribution can be parameterized by an injection momentum. So we will assume that this term is given as eta times N1 times U1 divided by 4 pi P square injected. And the injection is only going to happen at the injection momentum. So that's the reason for this delta term here. So the reason for this prefactor that I introduced here is the following. So eta is going to be the cosmic ray acceleration efficiency. So this is a parameter that is maximally 1 for maximal efficiency, but in general it will be smaller than 1. And if you now integrate the phase-space distribution over the momentum with this prefactor, you will have eta times U1 times N1. So this is the background density of, no, it's not I, it is 1, sorry, U1 times N1. So this is basically the convection, the total convection of particles coming from the upstream region of the interstellar medium that are convected into the shock. This is going to be the source term. And this prefactor here is derived to get the correct normalization here of this term. So now if I assume that this term here...
May I ask a question?
Yeah.
In the previous part, it's not clear to me why in the downstream region we could take this derivative equal to 0.
So in the downstream region, we basically assume that we have repeated scattering of particles, repeated scattering. So this is basically the shocked region. And this will basically make sure that you have a smooth distribution. So you would you will assume here, or we assume here, that the gradient of this distribution is equal to 0. I see. So this extends to the entire downstream region. We are only interested here in the vicinity of the shock. So this is the reason why I had this qualifier here. I could also just say that this is given by this condition. So this will be the condition in the entire downstream region.
Okay.
And you can, well, if you look back here in the downstream region, the only terms that you have are these two terms. There's no source term and there is no adiabatic loss term. And if del phi del z is equal to 0, then this is a trivial solution to this equation.
I see. Okay. Thank you.
Okay, yeah, thanks for the question. Okay, so we are almost done. If we are now use this injection term, we can look for the solution of this differential equation. And in the interest of time and to make a long story short, I will give you the final result. The final result is given as follows. So the solution of the above differential equation here is going to look as follows. Phi 0 is given as 3r over r minus 1. And I will tell you in a second what r means. Eta times n1 divided by 4 pi p injection squared. So this was the prefactor of the source term. And then I have here p over p injection to the power 3r divided by r minus 1. And the factor r here is defined as the ratio of u1 over u2. This is the ratio that we derived from the Rankine-Hugoniot jump condition, and for strong shock, this is going to be equal to 4. So you see now that in the phase-space distribution, we will get a power index. There should actually be a minus sign here. Sorry, it's a minus sign. So you see that for r equal 4, the spectral index will be 3 times 4 divided by 4 minus 1. So this is equal to 4. So this is the condition that you get automatically from this approach of diffusive shock acceleration without needing to specify what the diffusion loss and the acceleration time scale is. So the phase-space distribution, phi 0, is going to be proportional to momentum to the power minus 4 in the case of a strong shock. And that means if we are looking for the spectral density, which is related to the phase-space distribution via 4 pi over 1 in the case of relativistic particles, times p squared phi 0, then this is going to scale as energy pi 0 to the power minus 2. And this is basically the main outcome here of this exercise. Diffusive shock acceleration in the case of strong shocks will give us a particle spectrum in the shock that is scaling like energy to the power minus 2. Are there any questions at this point? So the derivation of this result is, of course, an idealized situation. You can look for next to leading orders in the shock environment. For example, you can look for the finite size of the shock. You could also look for the case that particles are not only injected into this in the vicinity of the shock, but also in a broader region. You can also look for injection of particles which are not monoenergetic, and so on. So all these conditions, all these extra additions to our model will give us modification to these final result, and this can also lead then to modifications of the spectral index that we would expect from diffusive shock acceleration. One very important fact that these next to leading order contributions will also affect is the maximal energy that we can achieve in this environment. Since we have been studying here the stationary condition, So this was here the stationary condition, which is time independent. There are no limitation on the maximal energy of cosmic rays given by the finiteness of the time scales. So the spectrum that I just derived is a power law that is basically extending to arbitrarily high energies. So this is also an unrealistic condition. We have already talked about the maximum energy of cosmic ray sources yesterday, and the simplest argument would be the geometry of the source, the Hiller's criterion, that's going to limit the maximal energy. And there are other cases, for example, the loss of particles from this environment via diffusion, or other energy losses in the environment that eventually limits the maximal energy. One thing that I mentioned is that if you put all these additional loss mechanisms into the Hiller's criterion, it turns out that supernova remnant shocks should not be able to accelerate particles to very high energies in the cosmic ray knee region, so energies exceeding 1 peta-electron volt. However, what you can see in these middle-aged, or this is rather a young supernova remnant, if you look at these X-ray images, you can actually see that there are some X-ray rims, which are basically here in the outer region of your supernova remnant shock. And I will, as I will discuss in a second, this X-ray emission is produced by relativistic electrons in the vicinity of the shocks, so electrons which are accelerated by diffusive shock acceleration. And the reason that you have these X-ray rims is coming from a feedback effect between these cosmic ray populations of leptons as they stream through the plasma. So you can have streaming instabilities of particles that feed back into the plasma. And this is a very important effect for cosmic ray acceleration, because this leads to an amplification of magnetic field in the shock environment. So if you increase magnetic fields by streaming instabilities, then you can, on the other hand, also enhance the maximal energy that you can achieve via acceleration of particles. So these streaming instabilities, feedback of cosmic rays as they stream through the plasma and enhance the magnetic field, seem to be very important to reach these high energies that we observe in the cosmic ray data. And for that reason, supernova remnants might indeed be the sources of cosmic rays going up to the cosmic ray knee.
I have one question.
Yeah.
Could you please tell me the power index of the cosmic ray before and after the knee?
Yeah, so I think I don't have a slide on that prepared for today, but what I can do is I can make a sketch. So the picture that we had here was you have the cosmic ray energy, and this would be e to the power 2.6 times the density of particles, and it will start out as a constant. And then you have here the knee, the second knee, and the ankle. And this will be a few PeV. This ankle will be a few EeV. So this is how the spectrum looks like. And so you wanted to ask what?
The power index before and after the knee.
Yeah, so this is e to the power 2.6 in this case. And I don't precisely know the power index just below the, just above the knee. I think if I remember correctly, it goes like e to the power -3.
Okay, so the in the previous slide, the -2 correspond to the shock wave acceleration. So there must be some other reason to contribute to another small index, right?
Right. So when we talked about the leaky box model, it's a very good. I thank you for this question, because it relates back to what we talked about earlier. So in the Leaky Box Model, we derived that the spectral index here should go like e to the power minus alpha. So this would be the spectral index from the source. And then you have here minus delta, which is coming from diffusion. Now, when we were looking at, for example, the boron to carbon ratio, you could motivate that the diffusion index delta should be of the order of 1/3. And this is actually what you would expect from Kolmogorov turbulence. If you go back to the study of the diffusion tensor in the first lecture. So that means now we have here a spectral index of 2.6. And we have here, we have to divide 1/3. So the spectral index of the source should be in the vicinity 2.2 to 2.3. Yeah. So this is larger than 2. So this is the spectral index that I motivated now for the ideal case of shock acceleration. But if you have so if you have weaker shocks, then this will modify the spectral index, and also other nonlinear processes on top of this simplified discussion will also modify the spectral index. And we believe that this is the reason why the spectral index is somewhat softer here than 2.
Okay, thanks.
Yeah. So the 2.6 is related to the injection, but only after we take into account loss from the galaxy. If we only have diffusive loss, this should scale like the rigidity dependence of the diffusion tensor. Okay, so this is all I wanted to say on cosmic ray acceleration and supernova remnants. I already showed you this beautiful slide of the Tycho supernova remnant in X-rays. So in the rest of this lecture, I would like to talk about radiative processes, which are important for high energy observations, such as X-ray observations. Yeah, so we basically, I will try to walk you through different radiative processes that we have to take into account in multi-messenger astronomy. And the X-ray emission that you saw in the case of Tycho supernova remnant, this was X-ray emission generated by synchrotron radiation. So in general, energetic cosmic rays, which can be electrons, protons, and also heavy nuclei. So these particles will interact with magnetic fields. In particular, during the acceleration process, you need magnetic fields, so you will automatically have this as a possibility to radiate, to generate radiation. But you also have background magnetic fields, background photon fields from other sources. Or, for example, the cosmic microwave background is a background that is always present in the vicinity of sources. So this could be some internal photon background or external background, for example, the cosmic microwave background. And you also have gas in the vicinity, so you have matter, which can also induce radiation. So the processes which are important for high energy gamma ray, particularly important for high energy gamma ray emission, so important for high energy gamma ray emission, also X-ray emission, are the following. So we have synchrotron radiation. So this is simply the radiation which is induced by the fact that cosmic rays, in particular electrons, are going to spiral around background magnetic fields. And as they spiral around these magnetic fields, they will get constantly accelerated towards the magnetic field line. And this is a source of radiation. So this is called synchrotron. Then we also have Compton scattering. So this corresponds to the scattering of photons. So you start with so you have a photon coming in from one side, which is then scattering with, let's say, an electron. And it will scatter with the electron and produce a photon. So this is an elastic process. So this is in general Compton scattering if the electron would be a particle at rest, so non-relativistic. In the case of relativistic particles, we will have Compton scattering, and in particular, if the energy of the electron is much, much larger than the energy of the incoming photon, the outgoing photon will have an energy that is larger. So h bar omega is going to be much larger than the initial energy of the photon. And in this case, we will also call this inverse Compton scattering. So production of high energy gamma ray radiation is inverse Compton scattering. Then we also have the effect of Bremsstrahlung. So Bremsstrahlung is a German word which means radiation caused by breaking. And so in this case, you consider the acceleration of electrons in the vicinity of background protons. And as the electron is accelerated towards the direction of the proton, it will also radiate. And this radiated energy, depending on the energy of the incoming electron, will also be high enough that you can observe this in terms of gamma radiation. And another process that we are going to consider, which is actually the most interesting one in the context of multi-messenger astronomy, is the production of pi zero production. So the production of pi zeros, this is going to happen in the presence of cosmic rays, for example, protons, which are scattering with other atoms in, for example, a gas. And if this is happening at very high energies, you will have an inelastic process. In this inelastic process, you produce a cascade of particles. So you can have multiple particles coming out here, which I indicate here by this X. And the particle which is most interesting for us here is the production of a neutral pion, because the neutral pion is an unstable particle. It's abundantly produced by hadronic interactions because it's a light particle. And this particle decays into two photons, gamma plus gamma. What's interesting about this process is you can also produce charged pions, which have about the same mass. For example, you can produce a pi plus here. And this pi plus is going to decay into a mu plus, so an anti-muon, plus a neutrino. And the anti-muon will then further decay into a positron, another electron neutrino, and a muon anti-neutrino. So you see that these type of hadronic interactions are not only a source of high energy gamma ray radiation in the form of the decay of pi zeros, but they're also a form of neutrino production. So whenever you have a mechanism at work that produces hadronic emission in sources, then these sources should also be sources of neutrinos. So the emission processes that are indicated here as 1, 2, 3. 1, 2, 3. So these are also called leptonic processes, whereas 4 is a hadronic process. Leptonic processes, they are always dominated by light cosmic rays, in particular leptons, electrons, and they will dominate the emission, whereas hadronic interactions are produced by high energy cosmic rays, which are nuclei. In the simplest case, you would have protons, but you can also have heavier nuclei that lead to production of hadronic gamma rays and also neutrinos. Are there any questions at the moment? Of course, you have also other processes which are of importance. For example, tomorrow, we will actually talk about interactions of cosmic rays and gamma rays with gamma ray backgrounds in the universe, in particular the cosmic microwave background. So you could have collisions of high energy gamma rays with background photons, leading to the production of a pair of E+ and E- electron and positron. Or you could have a scattering process of a cosmic ray with a background photon that produces a pair of electrons and positron. So this is also called beta Heitler. Beta. Sorry, my handwriting is not the best. Beta Heitler pair production. Of course, cosmic rays can also interact with the background via a photohadronic process. For example, you can produce here a hadronic resonance, a delta plus, which is basically a part of the isospin multiplet of hadrons, if you remember your particle physics course. And this delta resonance is not stable, it decays, and it can decay, for example, to a neutron and a pi plus, or it can decay into a proton and a pi zero. So these type of interactions of cosmic rays with gamma ray backgrounds can also be a source of hadronic emission. So it's not necessarily the background of gas which is important, it's also the radiation background that can induce hadronic emission. And you can also have photo disintegration processes. If you're looking at heavy nuclei with an atomic mass number A, they can also scatter with gamma ray backgrounds, and they photo disintegrate. For example, they can split off one nucleons, forming a nucleus with one less nucleon, and then you have here an additional nucleon coming out, which could be a proton and a neutron. Or you could have processes where you split up not only one, but also two nucleons. So you end up with something like this here. This process can also leave you with excited states. So the A-1 could be in an excited state, and this excited state can then de-excite and also produce a line emission of gamma rays from this de-excitation. But usually this is not so important in cosmic ray physics. Okay, I think this is all I wanted to say about that. So let me tell you a little bit more about our expectation for the energy spectra for the different leptonic processes. And here I will start with the synchrotron radiation. So this is a process that you already know, of course, quite well. And in particular on Monday, we talked about the gyro motion of charged particles in the background magnetic fields. So here again, we have a background magnetic field and a lepton, in this case, an electron that is going to perform a gyro motion around this magnetic field. We assume here that the momentum of the particle has a pitch angle with respect to the axis of the magnetic field. So the pitch angle is cosine theta, defined as b hat times p hat. And this pitch angle here in this picture would be here. Now, if you look at into the direction of the magnetic field, of course, the particle is going to perform a gyro motion along the magnetic field line. And this gyro motion will have a constant acceleration according to the Lorentz force into the direction of the magnetic field line. So that means the particle is constantly accelerated perpendicular to the magnetic field line. Now, from your electrodynamics course, you might remember that if you have a particle at rest, which is accelerated, then the total angular and also energy integrated power, so the energy, electromagnetic energy emitted per time via this accelerated particle, is given by the Larmor formula. So the Larmor power is given as 2/3 1/4 pi q squared, so the charge of the particle squared, times its acceleration. And in our case, acceleration in natural units will be b dot squared. So this is the Larmor formula in Heaviside Lorentz units. This is the reason why this additional factor 1/4 pi appears compared to what you find otherwise in the literature. If we are dealing here with electrons in the following, the charge of the particle will be identical to the electromagnetic charge. So you get here a combination e squared over 4 pi, and e squared over 4 pi is simply the definition of the fine structure constant alpha. So you can also rewrite this expression as 2/3 alpha times acceleration squared. So this is here the non-relativistic Larmor formula, basically in the rest frame of the particle. But of course, in the rest frame of the particle, the acceleration of the particle will not be identical to 0. So beta dot here will be the acceleration of the particle in its own rest frame. Now, if you look for the case of very energetic electrons, which are orbiting about the magnetic field, you have to look for the relativistic generalization, which you can basically derive from a Lorentz transformation, but we're not going to do this in that detail. So for relativistic particles, the Larmor formula in our reference system will look like this: 2/3 alpha, and then you have a factor gamma to the power 4. And then you have to distinguish between acceleration in the direction of the motion of the electrons and orthogonal to the motion of the electrons. So these two acceleration will come with different gamma factors. So parallel acceleration along the motion of the electron will have an additional gamma factor, gamma square here. And for the orthogonal case, there will be no further gamma factors. So this is the Larmor formula, the total power, energy per time emitted by synchrotron emission as particles are orbiting around the magnetic field. Now, what is the acceleration for the case of synchrotron radiation? We have introduced here the motion of electrons in the first lecture. So this was given as P cross omega. And omega is basically a vector pointing in the direction of the magnetic field with the normalization of the frequency of the gyro motion. So the length scale of omega is the Larmor frequency, which is given as EB over gamma m. So this is the, of course, the acceleration of particles here will only happen in the direction orthogonal to the 3 momentum of the particle. So there's no acceleration of the particle with static magnetic field. The acceleration can only happen in orthogonal direction to the motion. So that means for the synchrotron emission, the parallel acceleration is of course equal to 0. And the second term will be simply EB over gamma m squared. So if we put everything back together, we arrive at the following expression. So for relativistic electrons, the total Larmor power is going to be 2/3 alpha gamma to the power 4 EB over gamma ME squared. And this can be written in the following way: 2/3 alpha squared over ME squared 4 pi. And then we have here gamma squared B squared times sine theta squared. So the Lorentz factor that you have here, I forgot to include the pitch angle. So this acceleration here is of course projected in the orthogonal direction. So that means there is an additional factor sine theta squared here. And the sine theta squared term should also appear here. So this is the reason why this appears at the end. And now we can somewhat simplify this expression. First of all, the combination of alpha over ME. This is also known as the classical electron radius, RE. And this classical electron radius is of the order of 2.8 femtometer. And with the classical electron radius, we can also express the Thomson cross-section. We're going to study the Thomson process in a few minutes. So the cross-section of the scattering of radiation of electrons at rest, this is given by the Thomson cross-section, and the total Thomson cross-section is 8 pi over 3 times the electron radius squared. And this is a very large cross-section. This is of the order of 0.67 barn. So 1 barn is 10 to the power minus 28 meter squared. It looks small, but this is actually a very large cross-section in terms of particle physics, and that's the reason why it's called barn. Okay, using these expressions, let me bring up a new page here. I'm running out of space. So using these expressions, we can finally write the total power, PL, as 4/3 times the Thomson cross-section. And then I have a combination B squared over 2, gamma squared, beta squared. And this combination B squared over 2, this is basically the energy density of the magnetic field. So the final expression is 4/3 Thomson cross-section, energy density of the magnetic field times gamma squared, beta squared. Yeah, so this is power. That means that this is essentially the energy loss of the electron in time. So with this energy loss of the electron per time, we can define a new time scale. So this will be the synchrotron loss time scale, tau synchrotron. This quantity is defined by the energy of the electron divided by the total power radiated away by the electron. So this is the energy loss of the electron. And if you plug in the Larmor power that we just derived, you can express this in terms of you can write this as 4 times 10 to the power minus 4 seconds if the magnetic field has a strength of about 1 Gauss. And then this scales like to the power minus 2, because we divide by the Larmor power that scales like b squared. And then the total energy dependence will go like 1 over the energy. So this is for the case that the energy of the electron is at about 10 gigaelectron volt, so 10 to the power 10 electron volt. So you can see that if you have sufficiently strong magnetic fields of the order of Gauss, so this would be a field at the vicinity of the Earth surface, and if you have very energetic electrons, then this will cause a loss, a synchrotron loss timescale, which is of the order of a few hours. So a rather short timescale compared to astrophysical conditions. Yeah. Are there any questions at the moment? Okay. So the Larmor power is the integrated power. A more detailed calculation will also give you the spectrum of the emission, and we are not going to do this. I'm just going to show you how the energy distribution of the emitted photons look like. So this is here a plot that I took out of this review that I mentioned at the beginning of my my lecture on Monday, and so you see the spectrum, the energy spectrum of photons radiated away by single electrons with a given energy is going to be peaked at a frequency. So the peak here in the frequency, this is at about 0.3 of a critical frequency. And frequency here is, of course, equivalent to energy. So the critical energy, I have it somewhere here. So the critical energy of the photon is going to be 3/2 gamma squared EB over ME. And you can calculate that for the energy and the magnetic field that I just used for the calculation of the synchrotron loss time, this will be 6.6 electron volt B over 1 Gauss times energy over 10 to the power 10 electron volt squared. So the critical energy of the spectrum, which is related to the peak, so the peak energy of the spectrum will be at about 0.3 of the critical energy. The peak of the spectrum will scale as the energy of the electron squared. Okay, so this is the emission spectrum for a single photon. So what happens now in the case where I have a distribution of electrons, in particular electrons which have been accelerated by Fermi acceleration? So we are looking now at the spectrum of electrons, and the spectrum of electrons in terms of their energy will go like NE at some reference energy E0, and then you have E divided by E0 to the power minus P. And from diffusive shock acceleration, we would expect that P is very close to 2, as we just derived. Now, when you look back here at this figure, this is well, a spectrum that can be approximated here at lower energies by a power law and by some exponential suppression here at higher energies. For the sake of the following argument, I will assume that the energy distribution that is generated by a single electron is approximated by a delta function. And this delta function is going to peak here at the maximum energy. So for the sake of simplicity, I will approximate the energy distribution that I call n hat of an electron with an energy E as a delta function with some constant. I call it K times delta, and then here E minus E peak. And the peak energy will be some constant A times the energy squared. Yeah, so the more precise expression would be given by this equation. So the peak energy is about 1/3 of the critical energy, and the critical energy scales like this prefactor here with the energy squared. So this is all that's going into this prefactor alpha here. And for now, we don't really worry about the normalization constant K here. What we're interested in is now what is actually the outcoming photon spectrum if you have a population of sources that follows a power law. And this combined emission of photons, so n hat epsilon E, that was the emission of a single photon, a single electron. The emission of a spectrum of photons is given by the integration of the electron spectrum weighted by the photon spectrum of one individual electron. So this is simply delta K times delta E minus epsilon peak in our approximation. Now, epsilon peak, as I said, is going to scale here as A times E squared, and this is here an integral over E. So I can rewrite this also as K delta E N E E. And now I convert this delta function in epsilon to a delta function in terms of the electron energy. So this is just E minus the corresponding peak energy of the electron. And now I have to divide here this delta function by the derivative of the peak energy by the energy. And this is simply given as 2 times A. And this has to be evaluated at, 2 times A times E. And this has to be evaluated as at the peak energy. So this will be AE peak. So now you see I can evaluate this integral trivially. And the outcoming spectrum will look as follows. So this factor here gives me E peak to the power minus P. So this is the spectral energy, the spectral index of the distribution. And then I get another factor -1 coming from this additional factor 1 over E peak, which came into the game due to the derivative of the peak energy with respect to the peak photon energy with respect to the energy of the electron. So on the other hand, we know that the peak energy that should scale as the square root of the photon energy just by inverting this equation here. We know that the corresponding, so if you write this in terms of the peak energy, this is going to be the dependence of the peak energy in terms of the photon energy. So that means if we put everything together and if we simply ignore the prefactors that we introduced here, we see that the spectrum of a population, of a power law population of electrons will go like epsilon to the power minus p plus 1/2. So that's very interesting. If you look for the synchrotron emission, the synchrotron spectrum from astrophysical sources, and if you identify the power law index of this population of the synchrotron emission, you can use this observation to infer the underlying power law index of the electron population. So for the case that P is equal to 1, the power law index P plus 1/2 would be equal to, sorry, this is P equal 1, P equal 2. So the emission would go like e to the power minus 3/2. Okay, so this is synchrotron emission. And so synchrotron emission is going to give us typically strong X-ray emission of sources where I have cosmic ray electrons reaching energies of the order of tera-electron-volt, and magnetic fields which can be in the range of milligauss. Are there any questions on this? Okay, then let me progress with Compton scattering. So the Compton scattering story is basically identical to what I just said for synchrotron emission. I start again from the non-relativistic form of the Larmor power 2/3 alpha beta dot squared. But here I do not have constant acceleration along magnetic field lines. Here I'm looking for a scattering process in the non-relativistic case where I have a photon which is scattering with an electron into a certain direction with a scattering angle theta. So in the non-relativistic case, this is also called Thomson scattering. This is for electrons at rest. And we can use the Compton scattering formula to estimate the power. In the classical regime, so classical means that h bar omega, so the energy of the incoming photon, is much, much smaller than the rest mass of the electron. This is the regime of Thomson scattering. And in this classical regime, I can actually treat the incoming electromagnetic wave as a classical wave, and the acceleration of that the electron experience in the background of the magnetic field can be expressed by the following time average. So we basically have to average over one oscillation period of the incoming electric field of the electromagnetic wave. And this will be, I mean, for simplicity, I will assume that this is linearly polarized. So this will be sine square omega t, so the frequency of the electromagnetic radiation. And then I have E times E0 divided by ME. This will give me the acceleration of the particle in the background of the oscillating magnetic field of the incoming photon squared. And the time average will simply be E squared over 2 ME squared, E0 squared. So E0 is going to be the amplitude of the electromagnetic background radiation. Now I can again reorganize this Larmor power in the following way. I can write this as 2/3 alpha squared 4 pi 1 over ME squared. And now I have E0 squared over 2. And you can recognize that this prefactor here, this is to be identical to the Thomson cross-section that I introduced earlier. And the second part here, that is equivalent to the total energy density of the radiation. So this will be U gamma. So the total power which is emitted by the Thomson scattering of an electron at rest is simply given by the Thomson cross-section times the energy density of the background radiation. Very simple expression. Now, this Thomson scattering is, of course, not the situation that we would like to look for. We would like to look for the case that we have electrons at high velocity which are interacting with the background photons. And if you look for the scattering of a photon with an electron, you can first of all look for the scattered energy. So the incoming electron will have an energy epsilon. The outgoing photon will have an energy epsilon prime. And we can relate via energy and momentum conservation these two quantities. And we find that in the relativistic case, the scattered photon energy epsilon prime divided by the electron mass is going to be epsilon over me. This was the initial energy divided by 1 plus epsilon over me 1 minus cosine theta. So in the Thomson scattering case, epsilon, the incoming photon energy, was much smaller than the electron mass. So this factor here is a small factor. So in the Thomson regime, you see that epsilon prime is basically the same as the energy of the outgoing photon. But if epsilon is much, much larger than the electron energy, then the outgoing photon has a different energy. So this is then also called in the relativistic case Compton scattering. So this is still an expression where the electron is at rest, but Compton scattering is basically described by the relativistic generalization of this process. So we can now find the total power which is radiated away by a moving electron in the background of photons. And I'm going to give you the final result. We will not have the time to derive this result. So in the relativistic case, the total radiation, PL, so this is dE gamma over dt, is going to be given by sigma tau times the background photon energy density times gamma square 1 plus beta squared divided by 3. So gamma and beta will be the Lorentz quantities from the relativistically moving electron in the background. So if I now, so this is the energy, so the total power that is radiated away by the electron. So now if we want to look for the total energy loss of the electron that is moving through the background of photons, so energy loss of electron, so dEE over dt, that is basically equivalent to the energy radiated away by the photon. But we also have to take into account that the electron at rest will also have this contribution here, simply from the interactions with the photon. So that means the total energy loss of the electron itself is going to be this expression, but we have to correct for the non-relativistic contribution when the electron is at rest. So if we are now using this expression here, we arrive at the following sigma t u gamma. And now I have here a combination that goes like gamma squared beta squared over 3 plus gamma squared minus 1. And this combination here can be combined to 4/3 beta gamma squared. So the total energy loss of the electron is simply given as 4/3 beta squared, gamma squared, the Thomson cross-section, and the energy density of the background radiation. And that's very interesting because in the case of the synchrotron emission, we basically had the same formula. So this is here the energy loss of inverse Compton scattering. So energy of the electrons will be transferred to the photon population. In the case of the energy loss of synchrotron emission, we had the same expression that we derived in detail. But here, instead of the radiation, the energy density of the radiation, we simply had the energy density of the background magnetic field. So you see that the ratio of these two quantities is going to be U gamma divided by UB. Now, are there any questions at the moment? Okay, I hope you are still awake, at least. So we can here also now look for the loss time scale of synchrotron emission. Sorry, not synchrotron, but inverse Compton. Inverse Compton emission. Again, this is simply E of the electron divided by dE over dt. Now in the case of inverse Compton. And I can express this quantity in the following way: 10 to the power 15 seconds for a background radiation of the order of 1 electron volt per cubic centimeter to the power -1. And then this also scales like the inverse of the electron energy. And this quantity is normalized to 10 giga-electron volt. So here you see that for very energetic electrons, which are interacting with background radiation, the inverse Compton loss time can be quite long. The normalization here, 1 electron volt per cubic centimeter. This is typical energy density of the cosmic microwave background, so the background of cosmic photons. So this process for 10 giga-electron volt energies is quite long. At least it's much longer compared to the synchrotron loss of the same electrons in Gauss magnetic fields. Also in this case, we can look for not only for the total power, but also the power which is emitted in terms of individual photons. And here again is the outcome of this more complicated discussion. This plot here is normalized in terms of the energy of the incoming photon. So this expression that you see here at the bottom, this expression is, yeah, it's not good to write white on white. Let's use some red. This expression is the outgoing photon energy compared to the incoming photon energy. And the distribution of photons which produced by inverse Compton scattering is also going to peak at energies. And the peak of this distribution will be at about the average photon energy of this distribution, which is given by 4/3 gamma squared epsilon. So and epsilon zero is going to be the energy of the photon in the background field. And numerically, one finds that this energy can be expressed as 5 times 10 to the power 8 electron volts. In the case of background photons at electron volt energies, and again for electrons at 10 GeV, so 10 to the power 10 electron volt squared. So the inverse Compton energy for upscattered background photons is typically much larger than the synchrotron emission in magnetic field. And that's the reason why inverse Compton scattering is one of the candidate emission models for high energy emission of supernova remnants. What you can also see here is similar to the case of synchrotron emission. You can approximate the background, the emission of individual electrons by characteristic energy. That means if you now again look for the, so if you're looking for the emission of a population of particles, so this is completely analogous to the case of synchrotron emission. If you look for an electron population that scales like e to the power minus p, the corresponding inverse Compton emission of electrons will again go like epsilon to the power minus p plus 1/2. For the same argument that I gave you in the case of synchrotron emission, the peak energy scales like the square of the electron energy. So the corresponding emission of the combined synchrotron spectrum will go like p plus 1/2. Yeah, then in the last 5 minutes or so that I have left today, let me briefly say something about Bremsstrahlung, which is another important process. So this is something that we are not going to discuss in great detail because it's also more complicated. It has more degrees of freedom. So Bremsstrahlung happens if an electron passes by a background atom, for example, a proton, and becomes accelerated in the direction of the proton. And via this acceleration, it will also emit electromagnetic radiation. So we can estimate that if the electron is approaching a proton with an impact factor of the order of b, so this will be the distance, then the time it takes the electron to pass in the vicinity of the proton, this time scale is of the order of b divided by the velocity of the particle, so b over beta in natural units. And so the acceleration that the electron experience can be written as the Lorentz force divided by the mass of the particle. And this will be given as alpha over me 1 over b squared. So alpha was e squared over 4 pi. So this is the elementary charge of the electron and the proton. So this is the acceleration. And that means if we are now going back to the Larmor formula, the power again in the non-relativistic case was given as 2/3 alpha times beta dot squared. So this is here beta dot. And that means the power of this interaction of electron and proton will cost the following power. So this is 2/3 alpha and then alpha divided by me beta squared to the power 2. So this should scale like 2/3 alpha to the power 3, 1 over the electron mass squared, 1 over b4. Now the impact factor b, that is going to be a statistically distributed quantity, and it will depend on the typical distance of protons in your background that is traversed by the electrons. So you can estimate that typically the impact factor b, that will scale as 1 over the density of the protons to the power 1/3. So if you have 1 proton per box with a size of b cubed, then this is the way to estimate this. And we can also estimate a characteristic frequency. So the energy of the emission and this characteristic frequency of the emission, that is again related to the time that the electron is passing in the vicinity of the proton. So the characteristic emission epsilon should be of the order of beta over b in natural units. So that means that the Larmor power divided by epsilon should go like 2/3 alpha to the power 3, 1 over the electron mass squared, the density of protons divided by the velocity. So this is the approximation that we can make. And this is also the only thing that I'm going to say about Bremsstrahlung. It is sufficient to say that Bremsstrahlung emission of energetic electrons can transfer a large amount of energy to the photons. So the energy is basically limited by the maximum energy of the electron population. And then, of course, it depends on the density of the background, if this is a dominating factor to the emission of astrophysical sources. I think I'm going to skip the hadronic interaction for tomorrow. I think I do not have any time left. Let me maybe give you one example of the emission of supernova remnants. So here I give you one last example. This is a supernova remnant which is observed by the Hess Observatory in high energy gamma rays. Here the energies are above 250 giga-electron volt, and here on the right it's 2 tera-electron volt. This is the picture of the supernova remnant in gamma rays. And if you look for the spectrum of the emission, which is summarized here on the right-hand side, so you see the total number of photons per energy. This is here the observation of Hess. This is observation done by the Fermi satellite. I'm going to talk a little bit about this tomorrow. And you see that this emission can be fitted to 2 different types of models. One is a hadronic model. So this is the emission which is produced by cosmic ray collision that produces pions, neutral pions that decay into photons. But it's also possible, this is shown here in the lower plot, to model the spectrum in terms of a leptonic emission model. So here you see 2 peaks. This peak is produced by synchrotron emission of an electron population scattering with the cosmic microwave background. And the high energy peak is the inverse Compton scattering of this. I got it wrong. So this is the synchrotron emission of electrons with magnetic fields, of course. The high energy end is inverse Compton scattering of the population with cosmic microwave background. So you have these characteristic 2 peak emission of the leptonic processes, and you can see that the data can be fitted by both of these scenarios as long as you tune the distribution of electrons and protons. So what you need here is broken power laws of the cosmic ray and electron spectra, but you can reproduce the gamma ray emission in this way. So you see that the different emission processes that we talked about today, they allow to reproduce the spectral energy distribution of supernova remnants and also other sources in the universe. But there's always a high ambiguity because it's in many cases possible to fit these spectra with various assumptions, including hadronic processes and leptonic processes. But as I also said earlier, the hadronic processes, they are also characteristic for the production of neutrinos. So for that reason, the neutrino emission will become very important to distinguish hadronic from leptonic sources. And this is all for today. Thank you. Are there any questions?
I have one question. Could you go back a few slides?
Yeah. This one?
No. And the previous one? Oh yeah, this one.
This one?
Yeah. I can't recognize your handwriting. In the bracket, it's plus gamma square minus 1 or?
Yes. So this is so this here is gamma squared beta squared divided by 3. So this is coming from this contribution here. Then you have plus gamma squared, which is coming from this contribution. So the first two terms are just the original Larmor power. And then the minus 1 is coming from the fact that even electrons at rest will, photons will scatter with electrons at rest. And of course, this is not causing any energy loss of the electrons. This will just be a redistribution of the photon energy via the scattering process. So this is not contributing to the energy loss of the electrons. And this is the reason why we correct for this term here. And you can do the exercise. Of course, you have the relation that gamma squared is 1 divided by 1 minus beta squared. If you put this in, you will find that the final expression is given by 4/3 gamma squared beta squared.
Okay.
Yeah, sorry for my hand. Okay, any other questions?
I have one. Could you go to the slide where there was the star equation, the one in the very early part of the lesson?
Oh, you mean here, this one? The star equation?
No, not the other previous. Another one, exactly.
This one? Yeah, okay.
Yes. Then essentially we have to integrate around the shock. And essentially I don't understand then in the next passage where the term in the left-hand side is 0.
Because, so let me try to see if I, yeah, so basically you are looking now at, so you have this term that goes like U d phi over dz, right? This convection term. And so you will look at this term from both sides of these shocks. And well, we have already motivated that this term in the downstream region is going to be constant. So this will look like something like this here. So this is del phi over del z times u. We don't know how this looks at the moment on the right-hand side. So the velocity is higher, so you will get a boost, but then it maybe can start from this point. So the only thing, so this, I mean, this is just very qualitatively, yeah? This is here the shock, and these are basically the two conditions on both sides. So the only thing that we are needing now is if we are integrating here across the shock from minus epsilon, which I call O minus, and plus epsilon, which is O plus, then if these two quantities here are real valued, so well-behaved quantities, then as long as this this integration region goes to 0, then the contribution of this term is going to be 0, independent of how this exactly looks on both sides of this shock. Is that clear?
Okay.
I have the feeling this is not entirely clear. So let's assume you have like a function like this here. Yeah, so you have a discontinuous function that looks like this. It has a jump, and it goes like this here. So this discontinuity, if you're focused here on the discontinuity, and if you integrate this function from minus epsilon with respect to this location here and epsilon, then the total contribution of the integral of this region will be equal to 0 as long as epsilon goes to 0. And this is basically the same condition that we are using here. The other terms, for example, the source term that was scaling like delta z. So if we have a peaked contribution at the location of the shock, if we do the same exercise and we integrate around the position of the shock, then this will always give us a constant value regardless of the size of epsilon here. And also, yeah, and also the second term that contributes is du over dz, which is basically the difference of u2 over u1 delta z. This will also give us always a fixed contribution regardless of the size of epsilon here. But as long as the function is, I mean, less than infinity, yeah. So if this is a real valued quantity, then I can simply integrate over the small slice, and this will be equal to 0. That's the reason why this term here in this expression around the shock is going to be 0, and only this contribution and this contribution here and this contribution gives a term.
Okay, yes, thanks.
Okay. Then if there are no further questions for today, so tomorrow I will then focus on high energy neutrino emission and also talk about this very interesting multi-messenger relation that you can have between gamma rays and cosmic rays, and also recent observations of neutrinos with IceCube.
Okay, Markus, thank you very much.
Thank you.
And before